quick before we start. Are you ready for it?
Yeah.
Okay, I want you to try and tell me how many holes these are, okay? Ready? If I had 1 over 1, how much would that be?
1 whole 1?
Yeah.
Well, that's just 1 then, 1 whole 1.
1 whole 1 is 1 hole?
Because it says 1 whole 1.
Because how many 1s do I have?
1.
I've got 1, so I've got 1 hole. Right, okay. Alright, what about 2 over 2?
So you got 2 halves there. 2 out of 2 is 1 whole 1.
1 hole. Okay. What about 3 over 3?
So you got 3 thirds. If you got all the thirds, 3 thirds, 1 whole 1.
Is there 1 hole as well? Oh, okay, cool. What about 4 over 4?
Well, I know this one because you've got a picture of it up the top. 4 quarters, 4 out of 4. You've got 1 whole cake.
Okay. I'm not trying to be jokey or silly. This is actually really important.
Keep going, Mr. Blum. I think I'm getting the hang of it.
Okay.
But I'm not sure.
All right. Well, how about this? Okay. 1,000 over 1,000.
So that's like you smash the cake into 1,000 bits and you've got 1,000 of them. So you've still got the whole thing, one whole thing,
Okay.
just a bit smashed.
Okay, we'll end it on that note there. But it's very, very important to note that and to understand why I'm making it that really important statement, that when you have the same number over as a numerator over denominator, that would be considered as a whole full figure. Okay, 1 whole amount.
Because we said before about fractions that they are bits of something. But if you have all the bits, then you've got a whole 1.
Yeah, absolutely. So that is vitally important moving into this part of the lesson now. We're going to be looking at improper fractions and mixed numbers. And I think that's probably the most important thing to note, is that to understand what would make 1 whole. And once you do that, you'll be absolutely fine. I promise you. Let's move on and go on to these 2 pictures over here, which I think are best going to describe what we're going to be doing today. I'd usually show actual cakes to children in my class, but we're kind of constricted to technology today, but that's absolutely fine. We've got a cake here which is split into 4 quarters. Could you say, Mr. Still, that is 1 whole cake, do you reckon?
That's a whole cake.
Absolutely, yeah, okay.
You haven't obviously been at that cake yet?
No, I haven't. I've been at this one over here on the right-hand side, though. What about this over here? Have I got a whole cake over here?
Not a whole cake, yeah.
It tells me I have how much?
You just got some pieces. You've got 3 pieces out of what could be 4 pieces.
Yeah, I've got 3 pieces out of what could be 4 pieces. Interesting. So if I put that together, do you reckon it would look like this? I'd have 1 and 3 quarters.
1 cake and 3 quarters of a cake.
Yes.
Yeah.
Okay. So that's what we call a mixed number. I'm going to just put it over here. It's a number that contains a whole number and a fraction. So as you can see, this number has a whole and a fraction. A proper fraction is just when it's a fraction by itself, but this is a mixed number because it has a whole number with a fraction. And what we're going to look to do today is we're going to look to transfer between improper fractions and mixed numbers. Now, improper fractions looks like a normal fraction, but the numerator is in fact larger than the denominator. What does that mean?
Well, we've called that in the past a top-heavy fraction, haven't we?
Yeah. Well, what that means is that the fraction is actually worth more than 1 whole. It's not less than a whole. It's not what you call a proper fraction. It's an improper fraction because there are more than 1 whole.
And it looks improper, doesn't it? It looks not proper because it's weird to have that bigger number on the top, isn't it?
Absolutely. Sorry, I'm just going to agree. It's working. It's sounding weird. So let's go and start converting, shall we? But I'm not going to convert using any methods just yet. I'm going to show you. We're going to convert using an example because, to be honest, we've already been given the kind of pieces here to do our question. So that's pretty cool. So let's have a look. So how many pieces make 1 whole? 1. Should we count together, Mr. Saw? So there's 1 there. 2, 3, 4. So that means we have 4 out of a possible 4, which makes 1 whole. Didn't we say earlier that if the numerator and the denominator are the same, there'd be 1 whole?
Yeah.
So doesn't that kind of prove our point straight away? And what else do we have? We also have this amount over here, which is that 3 quarters. So if I add that 4 and that 3, which makes 7, and I remember my addition and subtraction lesson that you did, that we don't add the denominators because they are the same, would I be right in saying that the improper fraction is 7 over 4?
Yeah.
So that's perfect. So as you can see...
So what you're saying, Mr. Blum, is that 1 3 quarters
yeah.
It's the same as 7/4. They're exactly the same, they just look different.
Absolutely. So that 1 is 4/4, and that 3/4 is added to that 4/4 to make the 7/4. What we're going to do now is we're going to go into actually doing it more as a calculation than as looking at it as a pictorial example. I'm going to start the second one. I'm not going to start in the improper fractions numbers. I'm going to start mixed numbers to improper fractions. I'm going to give us a question, Mr. Sewell. I'm going to go 2 1/4, okay, is equal to what as an improper fraction? So first step is we look at, when you get a mixed number, is what is the denominator of the fraction that you're given, of the proper fraction you're given. So as you can see, that is the proper fraction of 1/4, which means the denominator is 4. So what I would say is that when I turn these two whole numbers into fractions, I will therefore make them over 4. Okay, so we found out earlier that 1 whole would be 4/4. So what would 2 whole numbers be? Do you reckon I'd add maybe another 4/4, Mr. Sewell?
Yeah.
And then don't forget as well, finally, my 1/4. So that's 1 whole number there, plus that's 1 whole number there, plus 1/4. So that's perfect. I think that's right. I think if I go 1 plus 1 plus 1/4, that's definitely 2/4. Are all my denominators the same? Well, I made it a point to make sure that all my denominators are the same. And now what I'm going to do is just add the 3 together. 4 plus 4 is 8, plus 1 is 9, and I get my answer of 9/4.
I think, I don't, you might hate me for saying this, Mr. Blum, but I think this one we could actually draw it quite easily, couldn't we? 4/4 plus 4/4 plus 1/4 is 9/4, because it's quite easy to draw those circles, chop them into 4.
So let's do that. I mean, please excuse my poor art skills, but we're going to go here. So that's 1 whole cake, 4 pieces. Cut it in. That's 1 whole cake, 4 pieces.
So that makes 8 pieces in total so far.
Pieces. Yeah, we've got 8. So that's going to be 8. And then we've finally got only 1/4 colored in over there. So we've got 8 4s plus 1 4, which equals, just as I did earlier, 9/4.
And there's nothing wrong with that being on your test paper in an empty space. If you need to draw the picture, draw the pictures.
Absolutely. 4 whole numbers and 1. I keep saying 1. Let's do 2/3. Okay. Let's do 2 more, and we're going to do 9 and 1/7. That'd be quite interesting. I keep doing 1. Maybe I'm going to do 4/7. Okay. We're going to convert these into improper fractions. Again, going by the methods and understanding. So first is understanding what the denominator is of the fraction that's given. So for the first one, it's 3, which means that these 4s are going to be 4 3/3s. 1, 2, 3, 4. Now if you understand this, you'd know that it would be 3 times 4. So therefore this is going to equal 3, 6, 9, 12. So it's going to be 12/3. 4 whole numbers is represented in improper fractions as 12/3.
Because
3, 6, 9, 12.
Anything more than 1 whole 1 is going to be a top-heavy fraction.
Absolutely. But I'm not finished yet because I need to add as well that 2/3. And that will give me my final answer of 14/3. Let's have a look here on the 9s. So I'm now going to go into a bit more of a method style. Can you see this 12 over here? Well, if I multiply 4 by 3, I'd get 12. And then I added the 2, didn't I, at the end? So 4 times 3 equals 12, plus the 2 equals 14. So shall we do it in that proper method, Mr. Sewell? So let's do it without counting all these up. I might do it both ways, but actually I'm going to now use just the adding of each individual whole number right to the end and actually just do the method. Now I'm going to show you the method. Multiply the denominator, 9 times 7, which is 63, over 7. Add the 4. And then your answer is 67/7.
So that's because in that 9 whole ones, you've got a lot of sevenths, haven't you? So in 1 whole 1, you've got 7. In 2 whole 1s, you've got 14. So you can do your 7 times table 9 times, can't you?
Yeah, exactly.
7, 14, 21, 28.
Can we do it like this? Yes, we can. We can go 7 over 7, 7 over 7, 7 over 7, 7 over 7. I'm regretting this now. 7 over 7, 7 over 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. You could do that and then add all of these 7s up together. But that wouldn't make sense because that 7 is a repeated addition, isn't it? So it's multiplied 9 times. So you need to make sure that you remember that.
We do say that times is just repeated addition.
So there you go, 67 over 7 is my answer. What about improper fractions to mixed numbers? Because it is differently done, but it's very simple to remember. So let's look at this one over here, this one 12 over 5. Now, the biggest thing you need to remember is that this sign over here, this fraction sign, actually means divide. Can you believe that? It actually means divide. If I give you the 6 over 3, you would tell me that it's 2 3 over 3s, right? It's 2 3 over 3s, which means, and we know that 3 over 3 is 1 whole and 3 over 3 is 1 whole, so that we know that 6 over 3 equals 2. But if I divide 6 by 3, what do I get?
2.
2. So that fraction sign is actually a divide sign. And if we understand that, when we're doing improper fractions, it's going to be nice and simple. So what we want to do is we want to take that 5, the denominator, and we're just going to go in the multiples of that until we get to the numerator. So in the case of 5 over 12, we're going to find out how many 5 over 5s are there in this 12. And that is by dividing 12 by 5. How many 5s go into 12? 5, 10. There are 2 5s that go into 12, but there's a little bit left over, isn't there? There's a remainder amount, and that is that 2 over there. So the answer is 2 and a fifth. How does this look in terms of fractions? You've got 1 5 over 5, you've got another 5 over 5, and you have a 2 over 5 as well. And that's what makes up that 2 and 2 fifths. 66 over 8. Let's try something slightly larger. Again, remember that is equal to the divide sign. So we say how many 8 over 8? We want to find out how many 8 over 8s there are. 8, 16, 24, 32, 40, 48, 56, 64. So 8 times it goes in, but it doesn't go in properly because there's 66. So 66 divided by 8 is 8, but there's also 2 left. 2 8s left. We're going back to the equivalence calculation, the equivalence video that you've probably previously watched. We need to find this in its simplest form. We can divide both the 2 and the 8 by 2, so you can get 8 and 1 over 4.